Now let's look at the constraints. Okay, so here we've already used this table. So check. Okay, and we'll go back to the problem at the beginning. Do we need to use this $750,000? This is the amount of order received. And since in the objective function we've already minimized the total cost, we don't really need to use this number because it's a fixed order. And as long as we minimize the total cost, then the total profit, which is this 750,000 minus whatever this total cost comes up with, then we will maximize the profit. Okay, so check. We already look at this, and we don't need to use it. Then let's look at this table. These two should be very familiar to you now, in regard to how to write the constraint out based on these. Okay, and here I like you guys to write the constraint yourself first. Okay, so write the constraint for the number of hours of wiring needed to make model 1, 2, 3 should be less than or equal to the amount of total wiring hours. Okay, and also the second constraint would be the number of hours used for harnessing to make model 1, 2, and 3 should be less than or equal to the 5,000 hours of harnessing available. This is exactly the same format as what we created for the Blue Ridge hardtop problem. So the resource used or resource needed need to be less than or equal to resource available. So please write these two constraints yourself. Okay, hope you are done. So I'll write this out here. Subject 2x1 plus 1.5x2 plus 3x3 need to be less than or equal to 10,000. Then 1x1 plus 2x2 plus x3 need to be less than or equal to 5,000. Okay, so the first is the wiring hours. The second one is the harnessing hours. And these two constraints represent resource needed or used need to be less than or equal to resources available. Okay, so these are the first group of constraints. Then let's go back to see if we need some other constraints. Okay, so these two rows already used. Check. We used these and also used these ones. Then what we didn't use so far are those numbers. These numbers represent the customer order that we have to fill. Remember, in this last sentence we said we need to fill this order. Okay, so no matter how many of model 1 you buy and how many you purchase, altogether they should fulfill this order of 3,000. Okay, so with this analysis we know that, okay, the number we buy for model 1 and the number we make and the number we buy add up together should fill this order. So that means should be equal to this one. Okay, so that gives us our third constraint, which is M1 plus B1 should be equal to 3,000. With the same logic, we can write constraints for the other fulfillment of model 1, model 2, and model 3. So the number you make and the number you buy for model 2 should be 2,000. Number you make and the number you buy should be equal to 900. Okay, so this is the second group of constraints, means total of lip rings should be equal to order number. Okay, now I've got a question here. For those signs, equal to means that we just fulfill the order. And can we change it to greater than equal to sign? Let you think about this. Okay, to answer this question, first let's think about what does greater than equal to sign mean. A greater than equal to sign here means we want to make and buy at least 3,000 Model 1 so that we can fulfill the order. Okay, and we make and buy at least 2,000 of Model 2, and we make and buy at least 900 for Model 3, so the order can be fulfilled. But people would think, is it economical to make and buy more than what is ordered? You think, no, it's not economical, right? So why should we use greater than equal to sign? Okay, and the reason is that, especially when we go to later chapter 6, when we set constraints on those decision variables to be integers, meaning that we don't buy or make a half slip ring. Okay, we always make an integer number of those slip rings. Here we don't impose those constraints because they use a different kind of algorithm to solve, and we'll talk about that later. Even though in this problem it makes perfect sense to impose those integer constraints, but we won't write it here. Okay. Especially when we impose those integer constraints, having equal to signs will be too restrict, and sometimes we may not be able to find a feasible solution. Okay, think about this. Last week we talked about graphical solution, and we talked about some special situations. When you have equations in your constraints, think about what the feasible region becomes. The feasible region becomes a line, right? Because of those equations. So that shrinks the possibility of finding a feasible solution. Because you may not be able to find a solution that satisfies all those equations, and it's within the feasible region. So if those constraints are inequalities, that improve our chance of finding a feasible solution. Okay, that means when the optimal solution is found, some of those left-hand side may not be strictly equal to the right-hand side. So this one may be, say, 3,200, and this one may be 2,000, and this one may be, say, 902, in order to find a feasible solution. Okay, and in this problem, if we change it to greater than equal to, it will still give us exactly the same result. Why? Because we've already got this objective function here, right? Our objective is to minimize the total cost. So as long as all of those constraints are satisfied, even if we change it to greater than equal to, if we can find a feasible solution at this straight equal to, the solution will be straight equal to. It won't, the left-hand side of those constraints won't go beyond what is required. Okay, because the objective function will force those M1, M2, M3, B1, B2, B3 numbers to be as small as possible to minimize the total cost. Okay, think about this again. We are saying that because of this minimization objective function, which will force these M1, M2, M3, B1, B2, B3 to be as small as possible. So Even if we change these signs from equal sign to greater than equal to sign, M1, M2, B1, B2, B3, M3, they will be as small as possible. So if we can find the solution at a strictly equal level, they won't be greater than that. Okay, but changing those signs to be greater than equal to sign improve our chances of getting a feasible solution. Okay, so we will talk about this in more detail and illustrate with more examples later this semester. Here, I'll just mention this for your information. Okay, and in general, we just want to have those constraints as less restrictly as possible to improve our chance of finding feasible solutions. And because of the objective function, they will have the same effect as equal signs. Okay, with that said, let's see, are there any more any more constraints that are missing? Yeah, the non-negativity constraint, right? So all the M and all the B need to be greater than or equal to 0 for all I goes from 1 to 3. And that's our model. Okay, so this is the model that we created for this problem.